Alright, hello there. I'm going to solve this difference equation, and you might recognize this as the Fibonacci sequence, in fact, where each term is equal to the sum of the previous two terms. Now, because this is a second order difference equation, you need to start with the first two terms given to you. So we're given y0 as 1 and y1 as 1 as well. So we're given the first two terms. So let's find the third term, that would be y2. Let's find that. Now y2 happens when n is 0. So let's just write over here, n is 0. And we get y0 plus 2, which gives us y2. So that's going to be equal to the previous term, y1 plus y0. So it's going to be equal to 1 plus 1. So we get 2. Now y3, using the same pattern, is equal to the previous term, which is 2, plus the term before that, which is 1. So we get 3. y4 is the previous term, which is 3, plus the term before that, which is 2, and that's 5. Normally I like to generate the first 5 terms. I'll just go one more term here. So that's going to be 5 plus 3 is 8. So I can write out my sequence like something like this. 1, 1, 2, 3, 5, 8, and so on. And it goes on to infinity. And at the end, when I get my general term of this difference equation, I will test it and see do I generate the same sequence, just to make sure that I got it right. So the next step now is to get the Z transform of both sides. Now, using the table of Z transforms, I'm getting the Z transform of each of these three terms. So the Z transform of this yn plus 2 is, well, actually, just let's write it like this. Z transform of yn plus 2 is equal to the Z transform of yn plus 1 plus the Z transform of yn. So I'm converting this difference equation now into a new equation. So what is this one? It's z squared times y of z minus z squared times y0 minus z times y1. So that's on the left hand side, and now the Z transform of yn plus 1 is z times y of z minus z times y0, and then the Z transform of yn is just y of z. Now I should substitute in y0 and y1. The first two terms are both 1, so they go here, here, and here. So my equation now looks like this. Z squared times y of z minus z squared times 1 minus z squared, or z times 1 equal to z times y of z minus z times 1 plus another y of z. I want to gather up all of my y of z's and put them on the same side. So I can actually add these. No, I can't. I'll bring them all to the left hand side, and then I'll factorize. So this comes over, minus z times y of z. This term comes over as well, so that'll be minus y of z. And all the other terms I'll bring to the right hand side. So this minus z stays. This minus z squared comes to the right, so that's plus z squared. And this minus z comes over and becomes plus z. So, oops, plus z. So actually these two, I could have cancelled here because it's minus z on both sides. But they cancel here. Doesn't make much difference. Now I'll factorize here, so take out y of z. It's a common term, so it goes in z squared minus z minus 1 times, and that's just equal to z squared. And now I can isolate by dividing across by this quadratic. A lot of our work is done now. However, normally, given a quadratic on the bottom, we will try and factorize, but this is an irreducible quadratic. It doesn't factorize. I'm going to show you a little trick to see whether a quadratic factorizes or not. the coefficients are a is 1, b is -1, and c is -1. So you know when you do the minus b formula, I should have written, hang on, c equal to -1. So a is 1, b is -1, and c is -1. Hopefully you can read that. It's a bit messy. And you calculate b squared minus 4ac, and you work out what that is. So that's going to be -1 squared minus 4 by 1 by -1. -1 squared is 1. Minus 4 by -1 is plus 4, which gives me 5. Now this is a positive number, so this does have two roots, this quadratic, if you were to plot it. However, it's not a perfect square. A perfect square is a number like 1, 4, 9, 16, 25, 36, and so on. These are perfect squares. So we cannot factorize it easily, but we can factorize it. It's just going to have square roots. It won't factorize nicely, but it will factorize. So using the minus b formula, let's find the roots. And we've actually done a lot of the work already. So the roots of it is going to be z equal to minus b. So that's minus 1. So it's minus 1. Plus or minus the square root of b squared minus 4ac is 5. I know that. All over 2a, which is 2 times 1. So that's 1 plus or minus root 5 over 2. Okay, so these are kind of awkward roots. That's what I was talking to you about, that it doesn't factorize nicely. Okay, so let's just write our factors now. We've 1 plus root 5 over 2 as one of the roots, so the factor is going to be z minus that. Gives me the first factor. And the other factor will be z plus that. No, it won't. It'll be z minus and the other factor will be z minus the other root, so that's 1 minus root 5 over 2. So it's always z minus the root, which gives you the factors. So z minus this root and z minus the other root. Now I'm going to have to use partial fractions. So I'll take a new page. Remember we had y of z is equal to, well, we had z squared on the top. So I'm going to take out a z so that I have a smaller degree on the top. And on the bottom now I have z minus the first root and z minus the next root. Now you could write these as a decimal and it would be fine. It's just a number. So it's just z minus some number, z minus some other number. These are distinct linear factors. So it's case 1. And you've done these loads of times. It's just a bit different this time because we don't have a number as such. We've got it written as a fraction with a surd. But otherwise we do the same procedure whenever we do a case 1 partial fractions. So just get rid of this page. It's my visualizer moving all over the place. And how do you do case 1? Well, you go something over the first guy plus something over the second guy. And our whole result then is going to be z, which is the numerator, will be a times this fellow on the bottom. I'll put a little bracket around it. Plus b times this fella here. 1 plus root 5 over 2. And now we choose values of z. So I'm going to make z equal to this first. Because I want this to disappear. This factor will disappear when z is that. It'll just be a times 0. So on the left hand side I get just z, 1 minus root 5 over 2 is equal to a times 0 plus b times z, which is 1 minus root 5 over 2. Take away 1 plus root 5 over 2. Okay, that looks a little awkward. But maybe there'll be some cancelling out. So 1 minus root 5 over 2 is b times, well, they have the same denominator at least, so I can just get a single fraction. On the top I'll have 1 minus root 5 minus 1, and this will be minus root 5 as well, all over 2. 1 minus 1, they cancel. Minus 5, root 5 minus another root 5 is minus twice root 5 over 2. These 2's cancel. So I have 1 minus root 5 over 2 gives me minus b times minus root 5. Hang on, where's this minus b coming from? It's not. It's just b times minus root 5. So then we have 1 minus root 5 over twice root 5 is equal to b. We should divide both sides. In fact, I'm dividing both sides by minus root 5, so I better put a minus here on the front, or I can go minus 1 plus root 5. Let's do it like that. So change the sign to both sides. Minus 1 plus root 5 over 2 root 5. Now you might be tempted to cancel those root 5's, but you can't because we have a sum here on the left. But maybe we don't need to do any cancelling. We found the value of b. Maybe we can work with it like it is. We've got this value here. We just need to find the a. And what's the quickest and easiest way to find the a? Well, I'll probably do the exact same thing, but I'll sub in this for z. So it'll be 1 plus root 5 over 2. And I'm basically doing the same thing again. So the left hand side will be 1 plus root 5 over 2 equal to a times 1 plus root 5 over 2 minus 1 minus root 5 over 2 plus b times 0. And again, these have the same denominator at least, otherwise they're a little awkward. So that denominator is 2. We've 1 plus root 5, take away 1, plus 5 minus minus would be another plus root 5. So very, very similar to the previous one. The 1's cancel. So we get actually is equal to a times 2 root 5 over 2, and the 2's cancel. So we have a times root 5. So it's very, very similar. So we get 1 plus root 5 over 2 root 5 gives me a. Okay, now I can write my y of z. Remember, I took the z out earlier on. I'm going to pull it back in again, and we'll put a z squared over. No, we won't. We'll have. I'll leave the. Shall I leave it out first of all? Remember, we have a z outside. I'm going to pull the z back in, right? So we'll have some constant over this plus some constant over that, and they'll both be multiplied by z. So the first constant is a. So that's 1 plus root 5 over 2 root 5 z over z minus 1 plus root 5 over 2. Plus b, which is, well, actually we can actually I will do plus. Minus 1 plus root 5 over 2 root 5 times z, and that's going to be over z minus 1 minus root 5 over 2. Okay, and now we can get the inverse Laplace transform of both to find y. N will be 1 plus root 5 over 2 root 5 times z over 1 minus that, according to my table of z transforms, is a to the n, where a is the thing in here. So that a must be 1 plus root 5 over 2. Plus minus 1 plus root 5 over 2 root 5 times this guy, 1 minus root 5 over 2 to the n. And that is my Fibonacci sequence. That should be the general term of the Fibonacci sequence. Okay, so I finished this video, but I had a really good idea, so I decided I'd add a little bit on. I said that you could test our result by subbing in values for n in our general term to see if we can generate the same initial terms of the Fibonacci sequence. And I thought, oh, it's really complicated to do that. If you put in 1 or 2 here, you have to multiply it all out. Of course, you can use a calculator to do it. And then I had this really great idea. Why don't you put it all in as a function with n as the variable, and then you just kind of write it out, the different terms of the function. So let's do that. So I'm going to upload my calculator here, Casio calculator. Drag it into Shot. Bring back my sheet. Bring up my calculator. And I need to do a function here. So mode table gives me a function. Now it's a bit of a tricky function to do, but you can maybe I'll pause the video and type it all in, or maybe not. I have to put this fraction in first. So that's 1 plus root 5 divided by 2 root 5. Of course, I only have to put this in once. That's the beauty of it. Multiply by, and now I'm going to put a bracket because this fraction will be raised to the power of n. So on the top I have 1 plus root 5. On the bottom I have 2. Close my bracket and raise it to the power of n. Now n in this case is going to be the x, which is the variable in the function. So that's going to change. I'll make it 0, 1, 2, 3, 4, 5 and so on. So now plus, pretty much something similar here. I'll put another bracket in here, put in my fraction, minus 1 plus root 5, cross and down, over 2 root 5, close my bracket, multiplied by, now opened up the bracket, this one's going to be raised to a power again. So what have we got? We've got 1 minus root 5. So it's great to have calculators to do this work, as you will see in a moment. We're going to raise this to the power of n as well. So to the power of, now of course our n again is x, it's the variable in our function. So everything's in, I should be able to hit equals now. Start at 0, I want to start with 0. And typically my calculators only go up to about 20 terms in a function. I don't think we even need 20, so I'll just go up as far as 10. And I'll step up in ones. And we should have the x is the term of the sequence, and on the right, f of x should be the term of the output. So the actual term in the sequence, 1, 1, 2. So the x is the n number. So 1, 1, 2, 3, 5, 8. Those are the terms that I generated at the start. 13, 21, 34. These are all the terms in the Fibonacci sequence. So this demonstrates that my formula is correct, and I'm very happy about that. Let's just zoom it a little bit So you can see the results there. There's all the terms there. So that's a nice little verification of my result, and I'm quite happy I had that brainwave. So that's all for this video. You could do this for any sequence, by the way. If you come up with a formula at the end for the general term, you could make a function on your Casio calculator and then start generating the terms of the sequence that way. As I said, I think it only goes as far as 20, maybe 20 terms. Let's double check. So equal from 0 to, let's try 20. Step up in ones. It's done it. Great. So we could find out if we wanted the 20th term of the sequence, 6,765. And that's when n is 19. So there you go. That's all for this video.